Okay, so hello and welcome back. So question number 7, we have for what values of x uh, 1 to 1 times this matrix, which is basically 1 to 0, 1 to 0, 2 0 1, 1 0 2 times another matrix 0 2 x is equal to O. So I think what I can do is that I can multiply this matrix by this matrix, and then multiply whatever I get multiplied by this matrix and equate that to O, and then we'll get some value for x. Meaning that this is a 3 by this is a 1 by 3 matrix, this is a 3 by 3 matrix. That means that I get a 1 by 3 matrix there, and then I will calculate basically the rest later. So let's do this part first. So 1 to 1 times this matrix, which is 1 to 0, 2 0 1, 1 0 2, and that is equal to a 1 by 3 matrix, which would be basically some matrix like this. So I have to multiply basically these values by this column. So 1 times 1 is equal to 1, 2 times 2 is equal to 4, 1 times 1 is equal to 1, and then I have this times this column. 1 times 2 is equal to 2, 0 0, and then I have 1 times 0 is equal to 0, 2 times 1 is equal to 2, and 1 times 2 is equal to 2. And then basically what I have is basically 4 plus 2 is equal to 6, 2, and 4. Now I can write, instead of these two matrices, I can write this matrix, and therefore I have 6 to 4 multiplied by 0, 2, and x is equal to basically O, which is a suitable 0 matrix. So this is a 1 by 3 matrix, this is a 3 by 1 matrix, and therefore you will get a 1 by 1 matrix. So I write it as a matrix containing only 1 0. And therefore you have 6 times 0 is equal to 0, plus 2 times 2 is equal to 4, plus 4x. That is equal to 0, which means that 4 plus 4x is equal to 0, which means that 4x is equal to negative 4, which means that x is equal to negative 1. I think the only value for x is therefore negative 1. If I'm not mistaken. We have a problem here, so we need to do something here. Okay. Well, okay, the answer is actually correct, so we can move to example number 8. Example number 8, we have if a is equal to, or exercise number 8. So we have a is equal to this matrix as 3, 1, negative 1, and 2, and you want to show that basically a squared minus 5a plus 7i is equal to 0, or O, you can say. You can basically you can basically put all of these one by one together, and then you can of course show that. So if I calculate a squared is equal to a times a, which is equal to 3, 1, negative 1, 2 times the same matrix, 3, 1, negative 1, and 2. And therefore you have 3 times 3 is equal to 9, and 1 times negative 1 is equal to negative 1. Then you have 3 times 3 is equal to 3 times 1 is equal to 3, 1 times 2 is equal to 2. And then you have negative 1 times 3 is equal to negative 3, and 2 times negative 1 is equal to negative 2. Then we have a negative 1 plus negative 1 times. So this row times this column is negative 1 times plus 4. And nine minus 1 is equal to 8. 3 plus 2 is equal to 5. That's negative 5. And 4 minus 1 is equal to 3. That is a squared. Now negative 5a plus 7a, I can write the equation as a squared minus 5a plus 7 times I is basically 8, 5, negative 5, and 3. And negative 5 times a, which is equal to 3, 1, negative 1, and 2. And you have also plus 7 times I. So I would be, in this case, 1001. Would be 1001. So you have, so this is equal to 8, 5, negative 5, 3 minus 5 times 3 is equal to 15, 5, negative 5, and 10. And then plus 7007. And then you have, so we can basically subtract first, meaning that 8 minus 15 is equal to negative 7. 5 minus 5 is equal to 0, negative 5 plus 5 is equal to 0, and 3 minus 10 is equal to negative 7. And if I add this to 7007, I will get basically 7 plus 7 is equal to 0, 0, 0, and 0. And that is equal to O, which is equal to RHS. And therefore, the identity is actually proved, right? Now, the next question that we have is question number 9. Question number 9 is, you want to find x if x negative 5 negative 1 times 1 0 2 0 2 1 2 0 3 times x 4 1 is equal to O. You want to find the value of x. So this is a 1 by 3 matrix. This is a 3 by 3 matrix. So you would get a 1 by 3 matrix. If I do this individually, I would get basically x negative 5 and negative 1. And then you have 1 0 2 0 2 1 and 2 0 3 is equal to basically a 1 by 3 matrix, something like this. So you have this times this, that would be x plus 0 minus 2, and 0, negative 10, 0, negative 10, and plus 0, and then you have 2x minus 5 minus 3, 2x minus 5 minus 3, which is the same thing as x minus 2, negative 10, and 2x minus 8. And if I multiply this by this matrix, I will get x minus 2, negative 10, and 2x minus 8, x, 4, and 1, is equal to, for example, let's say. Now, this is a 1 by 3 matrix, this is a 3 by 1 matrix, therefore you will get a 1 by 1 matrix. And so you have x minus 2 times x minus 10 times 4 plus 1 times 2x minus 8 is equal to, as a matrix, is equal to this matrix 0, which means that x squared minus 2x minus 40 plus 2x minus 8, and these two will be cancelled out, so that is equal to 0, and therefore x squared minus 48 is equal to 0, which means that x squared is equal to 48. 48, you can write it as 48, you can write it as 2 times 24, that you can write as 2 times 12, that you can write as 2 times 6, and that you can write as 2 times 3. So you have basically 2 raised to the power 4. So that means that basically 48 is 2 raised to the power 4 times 3. And if I take the square root of 48, that would be the square root of 2 raised to the power 4 times 3, which gives me 2 raised to the power 2 times the square root of 3, which is 4 square root of 3. So they can write this as, you can say that then basically x is equal to plus or minus 4 times the square root of 3. That was question number 9. The correct answer. Now question number 10. Question number 10, you have a manufacturer produces 3 products XYZ, which he sells in 2 markets. Annual sales are indicated below, and you want to make some calculations using the concept of matrix multiplication and that sort of thing. Okay, so this manufacturer has 3 products. So this is question number 10. So you have these products basically X, Y, and Z, and he basically sells them in 2 markets, in market 1 and 2. Okay. Now the annual sales are listed as, the annual sales of this producer is basically market 1 and 2, and the results are, and these are the products, and there you have 10,000, for example, 10,000, 22,000, and 18,000, and then you have for market 2 you have basically you have 6,000, you have 20,000, and you have 8,000. Which means that basically you have for market 1 the annual sales has been I don't know if this is the number of sales that they have made or what that is. We will find out. Now the question is basically the question that we want to answer now is basically A. If unit sales price of X, Y, and Z are unit sales prices of X is basically 250 rupees. 250 rupees for Y is basically 150 rupees or 151. Actually, that's 2.2 rupees 50 paisa, 1 rupees 50 paisa, and Z is 1 rupee. Is 1 rupee. Find the total revenue in each market with the help of matrix algebra. You want to find the total revenue. The total revenue in each market. That means that you don't want to basically the revenues of the two markets to be added together, but you want them to be reported separately, right? So, so I have these basically. I think this is the number of sales that I can assume that this is the number of sales that we have had in I think I can take this as product, for example, X, Y, and Z. I think I can make that assumption that this is product X, Y, and Z. And so that means that the number of sales of product X in market 1 has been 10,000, Y in market 1 has been 2,000, 18,000, and so on and so forth. And the same goes for product 2 relative to product X and Y and Z. And therefore, I need to basically, for market 1, I will calculate this for market 1, and then we will create one matrix for that, or one basically set of matrices multiplied together for that, and then we will learn how to do that based on one matrix, and then we will add the information of market 2 to the same set of calculation as well. That way we don't have to confuse ourselves, and also we will be able to do it basically effectively. Meaning that, so product A or product X in market 1, for example, now I'm just assuming that I have only one market. So if I had only one market, then I wouldn't have to worry about market 2. I would have to worry only about product X, Y, and Z and their unit prices, right? Which means that I can write, for example, I could write a matrix as, for example, 10,000 and 2,000 and 18,000, or before I do that, I could actually do a little experiment. I could write these as a matrix like this, or I could write it as a matrix like this. This would be a 1 by 3 matrix. This would be a 1 by 3 matrix. This would be a 3 by 1 matrix. On the other hand, these unit prices, I could write them as a 1 by 3 matrix like this, or a 3 by 1 matrix. I apologize for this. Or a 3 by 1 matrix. Now, if I wrote them this way, of course, a 1 by 3 matrix and a 1 by 3 matrix, of course, I wouldn't be able to multiply them together. These two matrices I could multiply together, this one, and the result would be a 1 by 1 matrix, which is what I want. On the other hand, I can take this and I could multiply it with this matrix, which gives me a 3 by 3 matrix, which I don't want, because I don't want 3. Basically, I want all of those to be added together, actually. And I could take the same matrix and multiply it by this matrix, in which case multiplication would simply not be possible, right? Okay, so that means that basically I am, if I can remember properly or correctly, I can use this matrix and this matrix together, meaning that I can use this matrix for the products and this matrix for the unit prices. So, and that is basically the way that you can always teach yourself how to do anything in mathematics and in physics. Meaning that whatever you want to do, basically you create a simple case out of that. You teach yourself, you always know how to do, you always know how to do simple things. More complicated things are just simply a more complicated version of those simple things. So if you know how to do those simple things, you can then basically add to the complexity and then make it more complicated. And the good news is that simple things you always know how to do. If you know how to basically logically proceed from simpler cases to more complicated cases, then you will always be able to do anything in mathematics or in physics. So I know that basically if I had only basically one market, these two matrices would be the proper structure of matrices for me. So I can erase all these two, and now what I can do is that I can add basically market 2 to the same matrices as well, meaning that I can say that, okay, so now these are for products XYZ for market 1. So what if I add these 3 products of market 2 to the same matrix as well, and write it as a 2 by 3 matrix, right? And then to this matrix as well, meaning that that's a 3 by 1 matrix, that would be a matrix like this, and I add the unit prices. Actually, I don't have to add the unit prices here, meaning that I can simply keep the unit prices as they are, because the unit prices are not changing. So I will have a 3 by 1 matrix and a 2 by 3 matrix. In this matrix, these are the unit prices for these 3 products, and this matrix simply becomes basically along this would be product X, this would be product Y, and this would be product Z, and this would be basically market 1, and this would be market 1, and this would be market 2, right? That way you can write down your matrices. And then this matrix would be basically a matrix like this. a 3 by 1 matrix that is related to the unit prices. So I can write now all of my all of these numbers based on this matrix pattern. So I write this as 10,000 and 2,000 and 18,000, and then I can write over here 6,000 and 20,000 and 8,000, and then I can multiply this matrix by these unit prices, which is 2.50, 1.50, and 1.00, right? And now I can simply multiply, and whatever I get is the revenue in that will give me basically, this is a 2 by 3 matrix, this is a 3 by 1 matrix. Multiplication is allowed, there is no problem with that. That gives me a 2 by 1 matrix, meaning that a matrix like this, and this would be the revenue, total revenue in market 1, and this would be the revenue, total revenue in market 2. That's what we were actually looking for, right? So that's how you can solve problems without confusing yourself, which takes a little bit of practice, but anybody can essentially do it if they are willing enough, and if they are doing mathematics even for a couple of years, even for 1 year, it's more than enough. You can teach yourself how to reason things out, how to do logical steps in order to solve problems, and so on and so on. Of course, this is a simple problem. So now I can do this matrix multiplication, and we said that we would get a 2 by 1 matrix. So I'm going to multiply this by 10,000 times 2.50. That would be 100 times 250. That would be basically 10,000 times 2.5 is the same thing as basically 1,000 times 25, which is equal to 25,000. So this would give me a 25,000. Then you have basically 2,000 times 1.5. 2,000 times 1.5, which is basically 200 times 15. 2 times 15 is equal to 30, and you have 2 zeros, that's 3,000. That is basically plus 3,000. And then you have 18,000 times 1, which is equal to 18,000. Right? So that is the first part here. And the second part is 6,000 times 2.5. 6,000 times 2.5. And one more thing that always works is that you don't want to rush yourself. If you rush yourself, you will either make mistakes, or you will make yourself nervous enough that you will not be able to solve the problem. For example, I do not really know what is this multiplication. I cannot do it in my head. I know that if I do it in my head, most probably I will make mistakes. So I just don't do it. I do it step by step. So that's the same thing as 600 times 25, and 6 times 25 is equal to 25 times 6, which is 120, and 30, that's 150. 150, and you have 2 zeros over here, so you have 15,000. 15,000. And then you have 20,000 times 1.5, which is the same thing as 2,000 times 15, which is the same thing as 30 and 4 zeros there. So that's 30,000. And you have 8,000 times 1, which is equal to 8,000. Right? So that is basically the calculation that we need. And then what we have is that we need to add these numbers together. So 18,000 plus, so this is 25,000, and that is 25,000 plus 18,000 plus 3,000 is equal to 21,000, and that's equal to basically 46,000. 46,000, and here you have 15 plus 8 is equal to 23,000. 23,000 plus 30,000 is 53,000. 53,000, and these are the revenues. This is the revenue for market 1. For market 1 in rupees. And this is the revenue for market 2 in rupees. Now let me check the answer here. $46,000 and $53,000, right? The part 2 of this question is if A and B, So if the unit costs of the above 3 commodities are if the unit costs of the above 3 commodities are 2.00, 1.00, 1.00, and 550 paisa respectively, find the gross profit. Okay, so now the gross profit is basically so these are the unit costs. So what the gross profit means is that, for example, you produce some product and it costs you some amount of money for the unit for one product. For producing one item of that product, it costs you, for example, so much money in order to produce that product. That is called the unit. That is called the unit cost price. That is called the unit cost price. The unit cost price, if you multiply it by the number of products that you produce, then of course you will be able to calculate the total cost price, right? The total cost price for all of the products that you have produced. And therefore, I need to calculate the total cost price here. So if I calculate the total cost price, and if I calculate the total cost price, and so that's the total amount of money that I have paid as a producer in order to produce all of those products. And this was basically the amount of sales that I made in rupees for market 1 and market 2. Meaning, as a result of selling those products, I got 46,000 rupees in market 1 and 53,000 rupees in market 2. That means that altogether I got 99,000 rupees, or nearly 1 lakh rupees for both of the markets together. So that means that if I subtract the total cost price from the total amount of money that I got as a result of selling all of those products, that gives me the gross profit, right? So now what I need to do is at first calculate the total cost price. the total cost price therefore is going to be equal to the number of products that I have, basically the number of products that I had here, right? The number of products that I had here, which is basically I have sold basically 10,000 and 6,000 for market 1 and 2. That makes 16,000 for market 1 and 2. Means that means that basically I have basically produced 16,000 items of product X, and I have created 22 basically items of product Y for the 2 markets, and 18 plus, that is 26,000 items of product Z for market C. So that's 16,000, 22,000, 16,000, 22,000, and what was that? The other one was 18,000. That's 26,000. That's 26,000 for, this is X, Y, and Z, all together for both of the markets, right? And this is the unit cost for these products. So now again, if I use the same matrix, meaning that if I use basically a 1 by 3 matrix and 1 by 3 matrix, and write all of these basically number of products here, 16,000, 22,000, and 26,000, and multiply it by the cost of producing of each of these products, which was basically 2, 1, and 0.5 in rupees. This will give me a 1 by 1 matrix, because this is a 1 by 3 matrix, this is a 3 by 1 matrix. That gives me a 1 by 1 matrix, which reports the total cost of all of the products that I have produced, X, Y, and Z all together. So that means that 16,000 times 2 is equal to 32,000, and 1 times 22,000 is 22,000, and 0.5, 26,000 is 13,000. And if I add them together, I get 45,000, 65,000, 67,000. That is 67,000. That is basically the total cost of production cost. Production cost for X, Y, and Z together, or all together. All together. All together, right? Now, the total revenue for all for market 1 and 2, the total revenue for market 1 plus 2, minus the total production cost, production cost is going to give me gross profit, which means that the total revenue for market 1 and 2 would be 46,000 plus 53,000, which is 99,000 rupees. 99,000 in rupees. Minus the total production cost over here was 67,000 rupees, which means that that is 32,000 rupees, basically gross profit. Gross profit. That is the answer for part B of this question, which has been given separately as 15,000 and 17,000. 15 and 17 is 12, 32, and 15,000, 17 was 32,000, which is basically the same number. They have calculated that separately for the two markets and then put them together. So that was question number 10. Now question number 11 is question number 11 is find the matrix X such that X times basically 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6 is equal to negative 7, negative 8, negative 9, and 2, 4, 6. And you can see that this is a 2 by 3 matrix. This is a 2 by 3 matrix. That means that, and of course, matrix X has to be a something by 2 matrix, because these two numbers have to be the same. And then this 2 comes from the number of rows of X, so this has to be a 2 by 2 matrix, right? So I define a 2 by 2 matrix as, for example, as if instead of X I write A, B, C, and D, and you can say that let X be equal to this matrix. Therefore, you can write A, B, C, and D times this matrix 1, 2, and 3, 4, 5, and 6 is equal to negative 7, negative 8, negative 9, and 2, 4, and 6. And then you can do the calculation. So this row times this column is going to give you basically, so this is going to be a 2 by 2 times 2 by 3 is going to be equal to 2 by 3 means something like this. So this is going to be A plus 4B, and this times this would be 2A plus 5B plus 5B. This by this would be 3A plus 6B, 3A plus 6B. This row times this would be C plus 4D, C plus 4D. This by this would be 2C plus 5D, 2C plus 5D, and 3C plus 6D, 3C plus 6D. And that would be equal to negative 7, negative 8, negative 9, 2, 4, and 6. Which means that A plus 4B is equal to negative 7, and 2A plus 5B is equal to negative 8, and 3A plus 6B is equal to negative 9. These are all the equations that you have that basically that contain only A and B. Okay, so now I can pick, but pick two of these formulas. For example, the columns basically 1 and 2 and 3. I can pick number 1 and write it as A plus 4B is equal to negative 7, and number 2, which is 2A plus 5B is equal to negative 8, and solve it as a system of equations, meaning that this is 1 and this is number 2. So multiplying 1 by negative 2, I have negative 2a, negative 2, 8, negative 2 times 4 is equal to negative 8 times b is equal to positive 14, and 2 I write it as it is. So that is 2a plus 5 plus 5b is equal to negative 8. Add them together, you will get negative 3b is equal to 6. That means that b is equal to 6 divided by negative 3, which is equal to negative 2. Now if I use equation number 1, I can write b is equal to negative 2, so a plus 4 times negative 2 is equal to negative 7, which means that a minus 8 is equal to negative 7, which means that 8 is equal to 1, right? Because 8 goes to the other side, it becomes 8 minus 7 is equal to 1. Now I can pick a couple of formulas here. For example, this one and this one. C plus 4d is equal to 2. C plus 4d is equal to 2. And also 2c plus 5d is equal to 4. 2c plus 5d is equal to 4. Call this, for example, 4 and 5. 4 and 5. If I multiply 4 by negative 2, I have negative 2c, negative 8d is equal to negative 4, and write 5 as it is, I will get 2c plus 5d is equal to 4, and therefore these two will cancel out. I'll have negative 3d is equal to 0. That means that d is equal to 0. And that gives me access to c, which is basically equation number 4. I can write c plus 4 times 0 is equal to 0 is equal to 2, which means that c is equal to 2. So over here I have a is equal to 1, b is equal to negative 2. So over here I have, so a is equal to 1, b is equal to negative 2, c is equal to 2, and d is equal to 0. And the matrix that we had was a, b, c, d, so this was matrix X is equal to a, b, c, d, which is equal to basically 1, negative 2, positive 2, and 0. That is your matrix X that we were looking for. And that was question number 11. 1, negative 2, 2, 0. Question number 12. Question number 12, we have if A and B are square matrices of the same order, such that AB is equal to BA, then prove by induction that AB raised to the power n is equal to B raised to the power n times A. Further prove that AB whole raised to the power n is equal to A raised to the power n for all. Okay. So we have something to prove here. And, I think I'm going to so A and B are matrices, are square matrices. This is number 12. A and B are square matrices of the same order. Such that AB is equal to BA, meaning that they commute. Okay, so basically AB are square matrices of the same order, such that AB is equal to BA. They commute. we want to prove by induction, that a times b raised to the power n is equal to b raised to the power n times a. Okay? And there is one more part to be proved here. We will prove that later. So basically we know that AB are square matrices of the same order, and we know that they commute. So the given in this problem is that we know that AB is equal to BA, and these are square matrices of the same order. We want to prove that this is the case. We want to prove that basically a times b raised to the power n is equal to b raised to the power n times a. So if you want to prove by induction, of course, then you need to check whether P of 1 is true. So for basically to prove that P of 1 is true, we have basically in this statement, if I set n is equal to 1, then 1 becomes basically a times b raised to the power 1 is equal to b raised to the power 1 times a, which means that ab is equal to ba. And that is true, of course, based on the given in this problem, and therefore P of 1 is true. Now we will assume that P of k is true. That is basically a times b raised to the power k is equal to b raised to the power k times a. And we to prove that P of k plus 1 is true, that is basically based on this, you can say that a times b raised to the power k plus 1 is equal to b raised to the power k plus 1 times a. So what you can do here is so this is what I have assumed. A times b raised to the power k is equal to b raised to the power k times a. So now I have to use I could use this, basically I could use what I have here, or I could use basically what I have here in order to prove that this statement is true. Well, let's see how we can do that. Okay, so if I start from the left hand side of this expression, so if I call this, for example, number 2, because I already have a 1 over here, so the LHS of 2 gives me basically a times b raised to the power k plus 1, right? That I can write as a times b raised to the power k times b, right? Now I know that from here, from this assumption that we made, is that b raised to the power k, a times b raised to the power k is equal to b raised to the power k times a. So I can write this as b raised to the power k times a and times b. And from here we know that from this assumption, from this, it's given that AB is equal to BA. So if AB is equal to BA, I can write B raised to the power K. Instead of AB, I can write BA. So over here, that is, the reason is that basically AB is equal to is equal to BA. And over here the reason is that is the assumption that we have made, right? Now this is the same thing as b raised to the power k plus 1 times a, and therefore you can say that a times b raised to the power k plus 1 is equal to b raised to the power k plus 1 times a, which is basically this statement over here, right? Which means that basically p of k plus 1 is true. So now we know that basically p of 1 is true, and we have assumed that p of k is true, and now we have assumed that we have proved that p of k plus 1 is true. And so you can say therefore by the method of, or the principle of mathematical induction, p of n is true. That is basically well, it's always basically a good idea to identify your p of n from the very beginning, because in the end it's hard to find it. Meaning that this would be basically your p of n, of course. So a times b raised to the power n, a times b raised to the power n is b raised to the power n times a is true, right? So that is true. That means that if you have two matrices A and B that commute, if you raise that is of course for all natural numbers n. That means that if you have two matrices A and B that commute, then if you write, and of course they are square matrices of the same order, if you raise the second matrix to the second matrix on the left hand side, you know what I mean. If you raise this matrix to raise to the power n, they would still commute, meaning that a times b raised to the power n would still be equal to b raised to the power n times a, which is of course something useful in many different cases, of course. But there is a problem here, and it's just not possible. I mean, I find it impossible, at least for me. You cannot remember all of these things whenever you need them. So I find myself, I mean, most of the time, I find myself, I mean, you have to go back and look at a couple of things, or prove a couple of things for yourself again when you need them. It's not like your mind is not like a computer, for example, that can remember everything and give you the right information at the right time, at the right place. Sometimes it doesn't work, but of course, the first step always is to familiarize yourself with the theorems that you need to know, and then later, if you need such a thing, you might actually recollect that there was something that I did over there, and now I could go back probably and I could find it, and then you might, and then you would find the right piece of information, right? Okay, so now the next part of this question is another proof. Let's do this proof and we will end this video here. Now the second part of this question is that you have basically A and B square matrices of the same order, A and B are matrices, or let's say square matrices. Square matrices of the same order. Such that AB is equal to BA, and you want to prove that A times B whole raised to the power n is equal to A raised to the power n times B raised to the power n for all n belonging to the set of natural numbers. So this would also be something useful, very useful actually, in many different cases. So now the given in this problem is that basically AB is equal to BA, and that the two matrices are square matrices of the same order. You want to prove that basically AB raised to the whole raised to the power n is equal to A raised to the power n times B raised to the power n for all n belonging to the set of natural numbers. So that would be your P of n. I'm going to use again the same principle of mathematical induction. Okay, so the first basically for the proof, the first step is basically to prove that basically P of 1 is true. To prove that P of 1 is true, we have n is equal to 1, and in this statement, let's call it, for example, let's call this number 1. In 1 we have basically AB raised to the power n is equal to A raised to the power 1 times B raised to the power 1 times B raised to the power 1, which means that AB is equal to A times B, which is true. Therefore, basically P of 1 is true. P of 1 is true. Now let's assume that P of K is true. That is basically put n is equal to k, and 1 becomes basically AB whole raised to the power k is equal to A raised to the power k times B raised to the power k. Now we want to prove that P of k plus 1 is true. That is basically n is equal to k plus 1, and therefore 1 becomes basically AB raised to the power k plus 1 is equal to A raised to the power k plus 1 times B raised to the power k plus 1. Which means that I want to prove this, right? Now, I know that basically if I start from, for example, this side of this equation, if I call this 2, for example, the LHS of 2 gives me basically AB raised to the power whole raised to the power k plus 1, which I can write as AB raised to the power k times AB. Now AB raised to the power k over here is equal to A raised to the power k times B raised to the power k. times b raised to the power k. And you want to multiply that by ab. Now, when you want to multiply these matrices together, you can of course, you know that matrix multiplication is not commutative, right? You know that matrix multiplication is not commutative. So I cannot write, for example, I cannot write a raised to the power k times b raised to the power k, for example, times, instead of ab, I cannot write, for example, ba. It is associative, but it's not commutative. Therefore, since I cannot do that, but I know that, for example, AB is equal to BA because A and B commute, which means that I can write A raised to the power K times B raised to the power K, and instead of BA, instead of AB, I can write BA because AB is equal to BA. Because AB is equal to BA. And now I can, since matrix multiplication is associative, I can write this as, for example, A raised to the power K times B raised to the power K times B times, for example, A. Because matrix multiplication is associative, if I'm not mistaken. Let me take a look at these. There were a couple of properties of multiplication of matrices, and we said that matrix multiplication is associative, meaning that basically the associative law in matrix multiplication, we said that AB times C is equal to A times B times C. And so that is called, basically, I can write this as the associative law, for example. Associative law. Right? So that is that. So based on that, I can write it this way, which means that this is going to be equal to A raised to the power K times, this is B raised to the power K plus 1 times A. And then I know that basically A raised to the power K times, I know that A raised to the power K times and in the previous part of the same exercise that we did, we proved something that we can use right now. We proved that basically for, if you have two square matrices of the same order, and if A and B commute, then A times B raised to the power n is equal to B raised to the power n times A. We already proved this in the previous step of the same exercise. Which means that I can write over here, you can see that you have A over here and over here B raised to the power n. I can write it as A times B raised to the power n. So that means that I can, and the same basically the same constraints that we have on A and B here, we have on the same theorem over here that we proved. So I can use this theorem over here, which means that I can write this as A raised to the power k times A times B raised to the power k plus 1. And that is because of the previous part of the same exercise. Right, so that is because of that, and then you can write this as A raised to the power k plus 1 times B raised to the power k plus 1, and that's what we wanted to prove, which means that basically A times B whole raised to the power k plus 1 is equal to A raised to the power k plus 1 times B raised to the power k plus 1, which proves that n of basically P of k plus 1 is true. So now we have shown that basically P of 1 is true, and then P of k we have assumed that it is true, and now we have proved that P of k plus 1 is true, and therefore by the principle of mathematical induction, P of n is true. That is, and P of n over here was basically AB raised to the power n. That is AB whole raised to the power n is equal to A raised to the power n times B raised to the power n for all n belonging to the set of natural numbers is true. And that's basically what we wanted to prove here. Now this video is getting a little bit too long. I'm going to end the video here, and then we will do question number 13, 14, and 15 in the next video. Thank you.